But gee, Leibniz, this is Sir Isaac. Tell me how you feel. Good morning, good afternoon, good evening. We are back and better than ever, talking the calculus stationary points part 2. Only 2 examples to do here. This is the second example from this section on stationary points. Find the exact position and nature of the stationary points of y equals x minus 2 times e to the negative x. Just a little side note here. When they say exact, that means you're not using your calculator to give a decimal approximation. So just keep that in mind. Okay, so to find the stationary points, we have to find the derivative. dy dx is equal to, thinking product rule, boys and girls. We have u and we have v, do we not? Okay, so that's going to be v du, so that's going to be e to the negative x multiplied by 1, so that's good. The derivative of u is 1, plus u, x minus 2, dv, so that would be e to the negative x times negative 1. So let's clean that up. So that would be e to the negative x minus e to the negative x times x minus 2. So that would be e to the negative x multiplied by 1 minus x minus 2. Holy smokes. Which is going to be e to the negative x times, let's simplify that, 1 minus x, so that would be a negative x plus 3. Okay. So now we need to set that equal to 0, and by the null factor law, we'll get to that in a second. So 3 minus x, we need to find out when that's equal to 0. So we're going to say e to the negative x equal to 0, or 3 minus x equal to 0. E to the negative x, that is impossible. There's no way we can get that equal to 0. So our only critical point is x equal to 3. So let's see what's going on there. And there's no restrictions on the domain, so the function is not defined or not undefined anywhere. So I'll put a 3 here. And let's see, where do we want to use? Let's use this one right here for our test point. For x greater than 3, we would have, well, no matter what, this is going to be positive. E to the negative x is going to be a positive fraction, no matter the value of x, as long as x is an integer. If it's a fraction, then that's another story. But not that it's going to be negative. It will always be positive. So let's see, let's choose 4. So a negative 4, that's going to be negative. And if we choose 2, a negative 2 plus 3, that is going to be positive. So we have a critical point at 3. Okay, now we need to put 3 into the original function. 3 minus 2 is 1. So 1 times e to the negative 3 equals e to the negative 3. So we could put e to the negative 3 here, or we could also put 3, 1 over e cubed. Okay, so what's happening there? What's happening at this point? Well, our function is increasing and then it is decreasing, which means that we have a local maximum. And that's all you need to do, okay, to answer this question. Okay, we have a local maximum. But let's take a look at it on the graph. Okay, we're saying it occurs at x equal to 3. 1, 2, 3. So right there. And that looks a little weird, but I've graphed the function correctly, you can see. And so let's do our little zoom box and see if we can get a little bit better of a look to see if it really looks like a maximum. So 1, 2, 3, and I think you can kind of see there, but maybe a little bit more will do. Maybe I'll just get in. Now this is 3 right here. So just so you know it, because it's all the other markings are going to disappear. And I think you can see it a little better, but now let's analyze the graph. Let's see, we think it's a maximum, so I'm going to go to the left of 3 and to the right of 3, and I get 3. 0.05. So let's just do 1 over e cubed. Let's see, I think I have to do that just to see if that's about right. So let's go here, and we'll do 1 divided by e cubed. Is that 0.05? Yes, it is. Okay. So there we go. Let's go back to the main menu. Oops. Home, current, and then we'll go to this, and that's our next function, and I like that view. Okay. So now we have shown that this is indeed a local maximum. One more example and we will be done. Find the greatest and least value of this function on the interval. The greatest value and the least value. Well, how can we do that? Well, we take the derivative, because we can find the global max, the local max, the global min, and the local min. Okay, so dy dx is equal to 3x squared minus 12x. Okay, and so I'm going to find my critical points by setting that equal to 0. So I factor out a 3x, and that would be x minus 4 equal to 0. And so that gives me x equal to 0 or x equal to 4. There are no restrictions on the domain. 0 and 4 are in the domain from -2 to 5. And so those are my only critical points. So we have 0 and we have 4. So let's do our sign diagram using our derivative. So -1, that would give me, let's see, that would be, let's use this right here. So -1, so that would be a -3 times a -5, so that's going to be positive. If I use 1, that's going to be a positive times a negative, which is a negative. And if I use 5, let's see, a positive times a positive is a positive. Okay? So here at x equal to 0, I have a local maximum from positive to negative. And at x equal to 4, so this is a local max. And then at -4, I go from negative to positive, or decreasing to increasing. So clearly that is a local minimum. A local minimum. Okay. But they're asking for the greatest and least value of the function, and they give us an interval. Okay? And if we don't have a graph, we have to check that interval. Let me show you what I mean. So let's say this is -2 and this is 5. We really don't know what this graph looks like, but we know at 0 and at 4 I have a local max and a local min, right? But it could be at -2, maybe it's like this. And then maybe the max, you know, it goes way up high, and maybe 5 is up here. Well, then the maximum would be here. The greatest point on the graph would be here, and the lowest point on the graph would be here. So we have to check the value of the function at the endpoints and at the critical points. So when x equals 0, what does the original function equal? That's going to be 5. Okay. And at x equal to 4, what do we get? So let's see, 4 cubed is 64, minus 6 times 16, 60, that's 96, plus 5. So that's going to be 96 minus 69, or 96 minus 70 is 26, one more is 27, so that's 427. -27, because that's a negative, sorry, -27. Okay, and then we got to check our endpoints to see if they're any lower or higher than this. What about -2? Well, let's see, let's replace it in here. And this is a legitimate non-calculator problem, so that's why I'm doing it like this. -2 cubed is -8. let's see, minus 6 times a positive 4 is minus 24 plus 5, so that's negative 32 plus 5 is a negative 27. So negative 2, negative 27. Okay, and then what about at 5? 5, let's see, 5 cubed is 125. So let's see, 125 minus, let's see, 6 times 25 is 150, minus 150 plus 5. So negative 25 plus 5, that's negative 20, so 5, negative 20. Okay, so we have to check this out. Our maximum value is going to be at 0, 5, because that's the maximum value of our function right there, 0, 5. So that is let's see, the greatest value of the function is 5, right there. And the least value of the function, negative 27, negative 27, and negative 20, the least is negative 27. So this is the greatest and the least. Okay? And let's check that out on our graph. I graphed it for you, but this could be a problem where you don't have a graph. Okay, so the greatest value is right here. Let's analyze the graph. Analyze graph. Maximum, we said, was at 5, which is correct. And the least value is negative 27. So let's see if that here. Let's actions. Let's do coordinates and equations. Let's just do the coordinates. Okay, so that's at the end, negative 227. I put that point there, and we think that's 27 as well. So or negative 27. So let's find the minimum. Left, negative 27. So both of those are global minimums, and the lowest point on this domain is indeed, or on this function is negative 27, or the least value. Okay. That is it. I am out, and we shall see you next time.